So, we're just gonna start off with a preview of calculus. What are the major problems that people were trying to solve when they created calculus? Because calculus is something that was created. And just to give you a brief, historical overview. Oops, what's wrong with my thing? Calculus was independently discovered by two different people. Oops. So, two different people independently discovered calculus. Not that you need to know this for the course, but it's an interesting story. You've probably heard of them. One of them was Isaac Newton, and the other was Gottfried Wilhelm, also known as G.W. Leibniz. These two people were rather amazing polymaths. So a polymath is someone who excels at a very high level in multiple things. Isaac Newton, I think, first discovered calculus in the 1660s. Interesting story. We've all lived through a pandemic. I think he was at Oxford or Cambridge, one of the two. And they had an outbreak, a plague pandemic. And he basically went home from college at the age of 18 and worked on a bunch of stuff by himself and invented calculus. It's pretty intense when you think about that. So he's 17, he started, the plague shut down the cities, there's all this stuff happening in England, the plague was going everywhere. People went back and retreated into their country homes, and he invented this by himself. He was actually working on a bunch of physics problems. Calculus is very useful for that. He was really interested in looking at the orbits of planets, and basically to solve those sorts of things, he had to come up with these calculus techniques. So pretty nuts. He was 18 or so. Leibniz was really famous. He was a logician, a lawyer, an engineer. He got his law degree first at the age of 16, and then self-taught himself math, and then basically in the 1680s also came up with calculus when he was in his 20s, early 20s, late teens, after he had got his law degree. Oh, he's also famous as a philosopher and theologian. Isaac Newton also did a bunch of other shit. He was a chemist, an alchemist, all sorts of stuff. But anyways, they both discovered it independently. Newton never published any of his work. He just kept it to himself. And then basically what ended up happening is that Leibniz was holy crap. He published this stuff in the 1680s and pointed out to everyone I solved a bunch of problems. And basically Newton was oh, this is bullshit. Or not. He basically a bunch of people saw Leibniz's. He was German. Leibniz was German. He posted it in Latin at the time. Everyone spoke Latin, and he posted it. He basically wrote this article, and it got published in a magazine that circulated everywhere. And a bunch of English people went to Newton. They're oh my god, have you seen what this guy has done? And Newton looked at it, and he's that bitch stole my work. And so basically, there's this really long running feud where who came up with it first. We now know that they published it independently, but at the time, people died in knife fights over it, about who should have precedence in having done it, which is really crazy when you think about it. People died over this, they were that upset. So yeah, anyways, you don't need to know this story, but I think this story is really cool. I've read several books about it. People have gone into it, and they found letters that Newton had written to people, weird things. So Leibniz at one point took a trip to England in his youth, and maybe was 50 miles away from Newton lived at the closest. And Newton had this conspiracy theory that he snuck into that Leibniz had snuck into Newton's house, gone through his secret calculus papers, stole the work, went back to London, returned to Germany, like looked over his notes and like stole everything from him. Like he actually went like sort of like paranoid and insane. So yeah, like really weird. Super cool story though, I have to say. But anyways, let's talk about like why did they come up with this? Like what were they trying to do? So there were two things that they were trying to do. There's something called the tangent line problem, and there's another thing called the area problem. We're going to start with discussing the tangent problem. So let's move the area problem out of the way, and let's discuss the tangent line problem. Okay, so the tangent line problem is also called the instantaneous rate of change problem. So like, what do we mean by that? So I'm gonna put in a graph here. Okay, so let's say this is our x and y axis. X and y axis. And so we have our x and y axis, and let's say that our function, we have a function. Okay, it's not letting me type. There we go. So we have a function of time which tracks the movement of an object. So what you have is like there's a little x right here, and let's say that's a starting point. Okay, and like your object starts moving away from that starting point. Okay, so like right here at this spot, that object is now some distance away from the starting point. This function will track how far that object is at that time. So let's put in a line. Let's say this is our function here. So at this point right here, let's say it has the coordinates 0, 1. Okay, so what does that mean? It means that at time 0, we started off a distance of 1 away from the point that we're measuring from. Let's say that we have another point over here. This is 1, 2. Okay, so what does that mean? At time 1, we are now a distance of 2 away from our point of reference. We'll add one more. This will be 2. Well, what should it be, given how I've drawn it? 2, what? That's a good question. Given how I've drawn this, what should that point be? 2, what? Yeah, cool. And how did you know that? Yeah. Exactly. Because it's a line, we know that if you, we know that the slope of this line is, let's just draw this. We moved right by 1 and up by 1, which means we have to move right by 1 and up by 1 again, right? Like, that's how lines work. Okay? So, if you're dealing with, so basically what's happening here is that we know that the object is moving away at constant speed. What do we mean by that? Like, each unit of time, we move a distance of 1 because the slope is 1. Okay, so what we find out here is that the slope of this line tells us something about the speed of the object. So the slope of the line is equal to the speed or velocity of the object. That's what we mean by instantaneous rate of change. Instantaneous rate of change is how fast is the object going, is basically how you can think of it if you're talking about like a moving object. Okay, so if an object is moving at a constant speed, like we get this graph like this, and the speed of the object is equal to the slope of the line. Okay, now the problem is, and let me put in another graph here. So now we've got, again, our x and y axis. But this time, instead of the graph being a straight line like that, it's going to be curvy. Now, because our graph is curvy, we don't have a slope anymore. So we knew that the speed of the object, or the instantaneous rate of the object, was constant because the slope was constant for our line. Now the question is like, hey, if we choose this time right here, let's call it time t equals 0. We know that the object was this far from our point of reference. Or if you choose some other time right there, let's call it t1. We know that at t1, our object was that far from our point of reference, wherever that is on the y-axis. It's like right here and right here. But we don't have an easy, quick way of figuring out how fast the object was going. Okay, wait, I want to draw this like more straight. It's like really upsetting me. There we go, that looks better. So let's call this distance d0, distance d1. Okay, so there's no line, so there's no slope, so we don't know how to figure out how fast the object is going. And here is our issue. You can actually figure out how fast an object is going at a particular point in time if you have this graph, if you were to draw something called a tangent line. Let's make that look better. That was like a really bad attempt. Let me draw the tangent line. There we go. Does everyone see that blue line right there? This blue line is called the tangent line at t equals 0. This blue line only touches the graph at that one point. And the slope of the line is equal to the speed of the object. Okay, like what I said earlier, the slope of the line is equal to the speed of the object. Like that's just something you have to take for granted now. It's just how it works. Now, we started off with a graph that wasn't a line, but if you draw the tangent line, the slope of that tangent line will be equal to the speed of the object at that particular moment. Okay. We have this one point on the line. When we're talking about a line, is it okay to only know about one point on that line? Put your thinking caps on for a moment. If I told you, hey, there's a line, and I just gave you one point on the line, is there any issue with that? Yes, exactly. How many do you actually need to find slope? Or how many points? Yeah. Okay, so here's the issue with you. You have this tangent line, you know that one point on it, and you want to know the slope of the tangent line because that would tell you the speed of the object. But you need 2 points. So like you have like a sad face, sad emoji, crying emoji or something. Okay, that's the issue here. Like the tangent line is a tangent at one point, you know it at one point, and you really want to know the slope of this line, but you're like, fuck, like, I need 2. The only way I can calculate slope is if I have 2 points. So that is literally the problem that they wanted to solve. They wanted to know the slope of the tangent line so they could figure out the speed of the object, but they only had 1 point. So let's just write this down. Here, this is the problem. The problem is you want the speed of the object. And you get that from the slope of the tangent line. But you only have 1 point. Okay, so people were acutely aware of this. They're like, okay, like, look, yeah, I get it. If we could figure out that tangent line and its slope, that would solve our problem, but like we can't because we only know the 1 point on there. And everyone just sort of like threw up their hands for a couple hundred years. Like people figured out like sort of how to solve it, but basically Leibniz and Newton, they figure out how to do this like always. Like prior to them, there were certain like cases where people were able to solve this problem, but they hadn't figured out how to do it in general. Okay, so they actually took a really genius crack at doing this. Or they basically figured out like a super genius way of solving this problem. So what they realized was instead of trying to figure out the tangent line, work with something called a secant line. So the tangent line touches at 1 point. So tangent line touches at 1 point. A secant line touches at 2 points. So let me draw in our another graph. So here's our x and y axis. Here's our function. Let's call it f of x. Okay, so let's say that you want the tangent line at this point, at x0. The tangent line looks like this. Okay, but you know that that's like, you're not going to be able to figure that out. You're not going to be able to figure out the slope because you only know 1 point. So you're like, okay, well, what do I do? So what you do is you realize that you can also choose another point. Let's call it x1. So now you have 2 points. You have the point x0 and you have the point x1. The secant line goes through both of them. So it looks like this. Okay, so let's label them. This one is the tangent line. It only touches at 1 point. This one is the secant line. It touches at 2 points. And what you find out is that the tangent line equals the instantaneous rate of change. What do we mean by instantaneous rate of change? We mean at a single instant. An instant is 1 point in time. That's where the 1 point comes from. Which is why the slope of this tangent line is equal to the speed at a moment in time. However, the secant line is equal to the average rate of change. and it's the average between those two different times. And so because we're talking about the average between two different times, you have to talk about the 2 points. Right? We said this point of time and this point in time. So in other words, the slope for this is equal to the average speed between x0 and x1. So the slope of this secant line, we give you the average speed between x0 and x1. The slope of the tangent line would give you the speed exactly at x0 or x0. So this is good because we have 2 points. Now you can actually calculate the slope. It's not the problem that you wanted to solve, but at least you are making progress. You're doing something. You're like, okay, well, I can actually calculate a speed now. So there's something called... Okay, but sorry. I'm going to move this out of the way. Let's move this area problem thing out of the way. We don't need it there anymore. So working with this, you realize that there's something called the average rate of change formula between x equals a and x equals b. A and b would be like these 2 points I was talking about. Instead of calling them x0 and x1, let's call them a and b. So if you want the average speed, and that's equal to the slope of the secant line. So that's right why I'm writing m sec. M stands for slope, sec stands for secant line. Between a and b, that is going to be f of a minus f of b over a minus b. Okay, so like just to redraw the picture, here's your x and y. Oops, let's make that look better. Here's your x and y axis. Here's your graph. Right here is x equals a. Right there is x equals b. You draw your secant line between those 2 points. Right here and right here. The slope of that secant line is given by this formula, and that gives you the average speed between that point and the other point. Okay, now obviously you wanted the slope of the tangent line, but like I said, you're making progress is the whole idea here. I'm going to pause for a moment. Questions? Also, if you ever need me to slow down, you should say, even though it's being recorded. But if anything ever occurs to you, please ask. So normally the way we do this, instead of using A and B though, is like slightly different, but hopefully this is making sense to you so far. So let me draw a different version of this graph. So here's your f of x. So usually we have 1 point right here, x equals a, and this is the point where you want to know the tangent line. So you want to know the slope of the tangent line at x equals a. Okay, so you want to know, you're like, hey, like, there's a tangent line right here. It looks like this. I would really like to know the slope of that tangent line, which we're going to call m tan. M for slope, tan for tangent line. Why do you want to know the slope of the tangent line? What would that tell you? What's like the piece of information that it would give you in the physics sense? Why are you curious about the slope of the tangent line? Exactly, yeah. The slope of the tangent line tells you the velocity of the object. That's what you're curious to know. Okay, and you're like, oh, shit, it only has 1 point. I can't figure out the slope of a line if I only have 1 point. So what do you do instead? You're like, okay, I'll find the slope of a secant line. So you choose some other point over here, and we're just going to call that point x. So you got a point A, and you have a point x. A is where you want to know the slope of the tangent line. X is just some other random point. Why is it just some other random point? Well, because you need another point. And what do? You find the slope of the secant line of that. And we have that formula. The slope of the secant line is equal to f of x minus f of a over x minus a. You plug it into the formula and bam, you get the slope of the secant line. Now, if you look at these two lines, what could you say about their two slopes? Like, if you look at the slope of the tangent line and the slope of the secant line, like, do you think that they're very similar to each other? Do they look very different? Like, what are your thoughts on that? What do we think? Like, if you look at that green line and that blue line, would you say that the slopes are similar to each other or radically different? I mean, they're sort of different, but they're also still fairly close to each other. Like, I mean, just for, what's it called? Like, if you look at this line, this has like a negative slope, the other two have positive slopes, right? Like, they could be way different from each other. I'd say they're fairly close to each other. And what they realized was, how about if I move this x point closer to A? So I'm taking this x point and moving it over to here. And I'm going to draw a new secant line with the closer point. So here's my new secant line. Oops, shit, I screwed up. This new secant line with the closer point is the slope closer to the tangent line or more different from it. Like, we start off with this one right here, and then now we have this one. So we have the first one, and then here's the second one. Is the second slope closer to the tangent line slope, or is it more different from the tangent line slope? It's closer. Yeah, exactly. And this is what they figured out. They figured out, this was their genius idea. They were like Leibniz and Newton, they were like, you start with calculating a secant line, and you just choose a point close to the point where you want the tangent line. And what ends up happening? The secant line slope is pretty close to the tangent line slope that you want. And that's basically what we're going to be doing. You're like, okay, cool, like, I choose 2 points. Like, I want my tangent line at A, but we'll find the secant line using A and some other point sort of close to it. Because when you end up drawing that secant line, you notice, like, oh shoot, that's just super close to the tangent line that I want. Okay? And basically, for the first half of Calc 1, we're going to be talking about how do you pull this off? Like, how do you somehow take this secant line, calculate its slope, but like do some magic to it, which is basically the calculus, that will actually give you the tangent line slope that you want. Okay, but it starts with this. You want to find the slope of the tangent line. You can't, so you first need to figure out something you can actually do. That's going to be the slope of the secant line. Okay. So basically, that's what the first half of Calc 1 is. We are going to be solving the instantaneous rate of change problem, also known as the tangent line problem. Okay, and this is a good place to take a break. So